Solving a triangle with the law of sines, problem type 2. In this video, we're going to be revisiting the idea of an oblique triangle. Again, remember, an oblique triangle is one that does not contain a right angle. We're still going to be looking at a naming convention of sides having lowercase letters opposite the angle that has the capital letter. And we have the 5 ways we can classify triangles. ASA and AAS, when you have 2 of the angles in a triangle, is what we talked about in problem type 1. In this video, we're going to talk about SSA, the situation where you have 2 sides as well as an angle which is not in between the 2 sides. In another video, we'll be looking at SAS and SSS, the cases where you have 2 sides and the angle in between, as well as the case where you have all 3 sides. Again, the idea here is that we know 2 of the sides of the triangle, and we know one of the angles, but it is not one of the, or it is specifically not the angle that is between the 2 sides we know. Rearranging the letters of this acronym, and you can really tell how much of a pain this particular type of triangle is. But one thing that is nice about the SSA triangle is that in what you are given, you automatically already have that nice pairing of angle and side opposite the angle. But we have one more side that we're going to be looking for. In this case, it's side little b. And we have 2 angles we're going to be looking for, angle A and angle B. With the information that we have, we are forced. There is only one piece of information that we're going to be able to find. The law of sines talks about the ratio of a side length to the angle, the sine of the angle opposite it. And so we have this nice pairing of side length and angle opposite it. We have another side length. So the first thing we have to do is find the angle opposite it, in this case, angle A. So we have the side length we know, which is 15, over the sine of the angle we know, which is 37 degrees. That's going to be equal to the ratio of the other side we know, 35, to the sine of the angle opposite, which in this case is angle A. I can do some manipulating here, cross product rule. And divide to get that the sine of angle A is 35 times the sine of 37 degrees, all divided by 15, which my calculator is quite happy to tell me is 1.404. Now, immediately, you should be noticing that this is a problem because I have a value of sine bigger than 1. And sine is the ratio of the opposite side to the hypotenuse in a right triangle. The opposite side is always smaller than the hypotenuse, so sine always has a value smaller than 1. This is one of the reasons that the SSA triangle lives up to its name. In fact, what we have discovered is that a triangle with side lengths of 15 and 35 and an angle outside of 37 degrees does not and cannot exist. It is impossible to get that third angle to actually meet. These measurements do not define a triangle. Right? So that's one thing we need to be aware of. It's possible when we are working through a problem involving an SSA triangle, the result is going to be, I'm sorry, that's not really a triangle. You're trying to fool me. That's not, of course, always the case. Let's take a look at an incredibly similar looking triangle. Right. This is again an SSA triangle. I've just moved the angle to the other side of the triangle. So we have angle A at 37 degrees. Angles B and C are unknown. Side C is 15, side A is 35. We want to know the two other angles as well as this third side down here. Once again, because we have an SSA triangle, it is guaranteed that we're going to have a situation where we have a side and the angle opposite it both known. And when we have a side and the angle opposite both known, we use the law of sines. We take the side we know, we divide by the sine of the angle opposite, in this case 37 degrees, and that's going to be equal to the other side we know divided by the sine of the angle opposite that, which in this case is C. Rearrange this equation I get that the sine of angle C is 0.257. So C itself is the inverse sine of that thing, which my calculator tells me is 14.9 degrees. Once again, though, we're going to run into trouble because it turns out, for reasons that we'll talk about later on this semester, that when you are dealing with sine, it's possible that this angle is not talking about an acute angle, but talking about an obtuse angle. It could be that the angle you're talking about here is 180 degrees minus 14.9 degrees. That hasn't come up in what we've talked about with right triangles, because right triangles don't have obtuse angles in them. This is only a thing that will happen with sine. Cosine has a different problem that comes up that we'll be talking about a little bit later. Right. But we have to check this. What is 180 degrees minus 14.9 degrees? In this case, that's 165.1. Sometimes both of the angles you get here give valid triangles. Sometimes only one or the other. Looking in this case, I know that there's a 37-degree angle in a triangle. If I add 37 plus 165.1, I'll end up with 202.1, which is more than 180. So this angle won't work because it would give you more than 180 degrees between the three angles of the triangle. So in this particular example, we end up with just one triangle coming out of it. It's possible to end up with one triangle. It's possible to end up with two triangles. It's possible to end up with no triangles. But now we know the value for angle C. We can use the fact that the three angles add up to 180 to figure out the value of B, and then use the law of sines one last time to figure out that last side length. This video is getting long enough, so I'm not going to go through those calculations. I think once we've got this far, the rest of it should make sense.